My name is Suchetana Chatterjee, and currently I am an assistant professor in the Department of Physics at Presidency University. So before coming to Presidency, I was in the US as a postdoc. So let me start from my bachelor's education. First of all, I grew up in my hometown in Berhampur, which is in Murshidabad district. And then in 1998, I joined as a BSc student in Presidency Physics, erstwhile Presidency College. And then after my BSc, I went to Indian Institute of Technology, Kanpur for my MSc, and I graduated from Kanpur in 2003. And then in 2003, I went to University of Pittsburgh to pursue my doctoral studies in physics. And I did my PhD under the supervision of Professor Arthur Kozlowski. And I worked on the Sunyaev-Zeldovich effect, and then I got my PhD in 2009, and then from 2009 September, right after I defended my thesis, I was a postdoc at Yale University from 2009 September to 2012 April, and then from 2012 May through 2013 October, I was again a postdoc at University of Wyoming after I joined Presidency University in 2013, November 2013, and I have been pursuing that work since then. The Jeans wavelength, we define the length scale. এই length scale এর মধ্যে যদি এর থেকে বেশি ম্যাটার থাকে বা এর থেকে বেশি ডেনসিটি থাকে তাহলে you will get collapse. Otherwise, there will be an interplay between the pressure term and the gravity term, and you are going to get oscillatory solutions. Okay? কি বাবা? Right. K যেটা হচ্ছে wave number আর wavelength 2 pi by 8. That was the wavelength, the Jeans wavelength. Right? Lambda G. Similarly, here also, if you look at the equation, দেখো exactly এক জিনিস আসছে. The only difference is s square. তাহলে এখানেও আমরা একটা Jeans wavelength define করছি, except now we have to define a co-moving Jeans wavelength, right? So we can come up with a Jeans wavelength defined as this. We can write Cs square kj square by s square equal to 4 pi g rho, and this is the co-moving Jeans wavelength. Okay? Co-moving Jeans wavelength. Everything is same except this factor of A that comes. And here you have delta K double dot. This is the Hubble drag term. This is the Hubble drag term. You have A dot over A, and this is the term where you have. So now I can write the equation in terms of the Jeans wavelength. Delta K double dot minus twice A dot over A delta K plus I'm going to take Cs square over s square outside the bracket, and I'm going to write s square 4 pi g over g rho ke ami likhte pari Cs square kj square by s square. So this I can write kj square times delta k equal to 0. Okay, so this is the growth equation, right? This is the growth equation in Fourier space. Now the question comes, কি হলো? কি প্রশ্ন আছে?
আমি জিজ্ঞেস করছি কে যেটা ওটাতে co-moving Jeans wavelength দিতেছে, কে যে তো ওয়েভ নাম্বার।
হ্যাঁ, ওয়েভ নাম্বার, সেটাকেই ওয়েভ নাম্বার বলে। তুমি ওটাকে ওয়েভ না, আমি যে বলছি Jeans wavelength সেটা না বলে তুমি বলো ওটা Jeans ওয়েভ নাম্বার, কোনো অসুবিধা নেই। যেহেতু যখন কসমোলজিতে সব অ্যানালিসিস ফোরিয়ার স্পেসে করা হয় তখন ওয়েভ নাম্বারকেই লোকে ওয়েভলেংথ বলে। For us now, the K space, the Fourier space is more dear to us. Okay, so this is how the growth equation looks like in an expanding universe. Now solving this equation requires what? প্রথমত আমাদের জানতে হবে এই a জিনিসটা, how is this a varying as a function of time, and that will be determined by what? The Friedmann equations. So that will be determined by the content of the universe, right? So that's something we have to know. And of course there is another problem in this equation. The A equation to দেখো depends on K, right? What is K? K is some inverse. K is proportional to 1 by L, right? So K is determining এ লেন্থ স্কেল। তার মানে কি? তার মানে হচ্ছে যে আমি যদি গোটা ইউনিভার্সের কথা ভাবি, তাহলে হোয়াট ইফ আই নাও সলভ দিস ইকুয়েশন ফর এভরি সিঙ্গল ভ্যালু অফ কে। আমি কে প্রথমত ইকুয়েশনটা নিউমেরিক্যালি সলভ করতে হবে, because you have the expansion parameter, you have this complicated equation. You cannot find an analytic solution, but you can find a numerical solution, and that's so easy. That's pretty easy to do. All of you are learning computational physics, you can solve it. So when you solve this equation, what you are going to get is how the delta k corresponding to each k, that means these k's are called modes, amplitude. You all know that. This is again a very field theory or field theory idea. That now you can imagine যে প্রত্যেকটা k mode মানে রিয়েল স্পেসে তার করেসপন্ডিং একটা লেন্থ স্কেল আছে। তার মানে আমি এখন দেখতে চাইছি যে আমার ইউনিভার্সে যে ইনফিনিট নাম্বার অফ লেন্থ স্কেল আছে, সেটা 1 মিলিমিটার হতে পারে, 10 পারসেক হতে পারে, 500 মেগাপারসেক হতে পারে। How are all of these scales, how are density perturbations in each of these length scale growing as a function of time? Okay? So what I can do is I can find out delta k as a function of time for different k modes, k1, k2, k3, so on and so forth. কথাটার মানে বুঝতে পারলে? That means I am seeing how the density fluctuations in each length scale is growing as a function of time. Now এই ইকুয়েশনটা তো আমরা অ্যানালিটিক্যালি সলভ করতে পারবো না, কিন্তু there are certain limits. একটা জিনিস তারপরেও মনে রাখো যে এই গোটা যে ফর্মালিজমটা আমরা করেছি, that is based on linear perturbation theory. So this is a linear equation, right? So when the perturbations are very small, but all of you know if these deltas grow as a function of time, then there will be a time when এই যে আমার কন্ডিশন ছিল যে আমার ওভার ডেনসিটি much less than 1, that will not be valid, and we can never use linear perturbation. প্রথমত ডেল্টা much less than 1 এর থেকে যদি আরেকটু বেটার হয়, ধরা যাক ডেল্টা less than 1, তাহলে তোমাকে যেটা করতে হবে ফার্স্ট অর্ডার অ্যাপ্লাই করতে পারবে, সেকেন্ড অর্ডার পারটারবেশন থিওরি, থার্ড অর্ডার, এরকম করতে করতে একটা টাইম আসবে যখন you can no longer use perturbation techniques at all, and then you have to really do numerical solutions, or you cannot really get into academic analytic form, and you have to solve them numerically, or you have to run simulations to know how the deltas, how the over density or how the density perturbations grow as a function of time.
এটা কি নন লিনিয়ার রেজিমে গেলে মোড মিক্সিং হতে পারে? মানে এখানে যেরকম, আচ্ছা এখানে যেন মোড ইন্ডিপেন্ডেন্স।
হ্যাঁ, ইটস আ ভেরি গুড পয়েন্ট। একটা জিনিস দেখো, খুব ইন্টারেস্টিং পয়েন্ট, এই জিনিসটা ফিজিক্যালি আমাদের বুঝতে হবে। প্রশ্নের প্রশ্নটা এই ইকুয়েশনটার দিকে তাকাও, এই ইকুয়েশনটাতে আমি এখন প্রত্যেকটা নিউমেরিক্যালি প্রত্যেকটা কে ভ্যালুর জন্য আমি এই ইকুয়েশনটা সলভ করতে পারি, কিন্তু আমার যদি ডেল্টা অনেক বড় হয়ে যায়, যে এই যে ডেল্টা যখন much less than 1, তখন তো এই ইকুয়েশনটা ভ্যালিড, কিন্তু ডেল্টা যখন ডেল্টা যখন অনেক বড় হয়ে যাচ্ছে, ডেনসিটি ফ্লাকচুয়েশন যখন অনেক বড় হয়ে যাচ্ছে, তখন কিন্তু বিভিন্ন যে লেন্থ স্কেলের কথা আমি বলছি, 1 মিলিমিটার, 1 পারসেক, 500 মেগাপারসেক এন্ড সো অন এন্ড সো ফোর্থ, তারা কিন্তু আর তখন ইন্ডিপেন্ডেন্টলি গ্রো করতে পারবে। কথাটার মানে কি? কথাটার মানে হচ্ছে যখন ধরো যখন আমার এইটুকু এত বড় সব যখন ইন্ডিপেন্ডেন্টলি গ্রো করতে করতে হঠাৎ দেখা গেল আমার এই ছোট জায়গায় প্রচন্ড বেশি মাস কনগ্লোমেরেশন হয়ে গেছে, তখন ওই ছোট জায়গাটার এফেক্ট এত বড় স্কেলের গ্রোথটা কিভাবে হবে তার উপর পড়বে। বুঝতে পারছো কি বলছি? অর্থাৎ ডিফারেন্ট হচ্ছে, সেটা হচ্ছে যে if there are different length scales and the perturbations are very small in all of those length scales, then they can grow independently without affecting each other. যে প্রেসিডেন্সির অ্যাস্ট্রোল্যাবের মধ্যে কি ঘটছে সেটা ইন্ডিপেন্ডেন্টলি ঘটছে কম্পেয়ার টু হোল অফ ক্যালকাটা সিটি, কিন্তু হঠাৎ করে প্রেসিডেন্সির অ্যাস্ট্রোল্যাবের মধ্যে যদি একটা সুপারনোভা একটা ব্ল্যাক হোল বসিয়ে দেওয়া হয়, then it's going to affect the dynamics of the Calcutta city, right? So that you have to, so that means I am now having a large perturbation in even a small scale or a different scale, and that can affect other scales. Okay, so that is called mode mixing or mode coupling. Mode mixing or mode coupling, mode mixing, mode coupling, and then you cannot have any linear equations. The equations become absolutely non-linear and completely not soluble, and analytic কোনো form, closed form করা সম্ভব নয়, তখন you have to run.
না মানে এটা নিউমেরিক্যালি যখন করি মানে when delta is greater than 1 or something like that, সেক্ষেত্রে এটা হবে, সেটা মানে সেটা জানি, মানে সেটা জিজ্ঞেস করি না। আমি যেটা জিজ্ঞেস করছিলাম সেটা হচ্ছে যে আপনি এটা বললেন যে ডেল্টা লেস দ্যান 1 বাট নট মাচ মাচ লেস দ্যান 1, সেক্ষেত্রে সেকেন্ড অর্ডার থার্ড অর্ডার পার্টারবেশন ইউজ করব, তখনও হতে পারে, তাই তো? আচ্ছা,
So there is no hard and fast rule. যতক্ষণ না তোমার মোড মিক্সিং হচ্ছে না, তখন হয়তো তুমি সেকেন্ড অর্ডার বা থার্ড অর্ডার করে বেঁচে গেলে।
হ্যাঁ,
কিন্তু মোড মিক্সিং হতে থাকবে তো,
আরো হায়ার এন্ড হায়ার অর্ডারসে যেতে হবে।
তখন you will have, তোমাকে দেখতে হবে যে হোয়াট ইজ দ্য অ্যামাউন্ট অফ নন লিনিয়ারিটি।
ঠিক, হ্যাঁ।
সেই নন লিনিয়ারিটি যদি খুব বাড়তে শুরু করে, তখন perturbation theory totally fails. Okay, then you have to do simulations and completely numerical stuff. কিন্তু আমরা তো এটা বলছি যে আমরা অ্যানালিটিক্যালি সলভ করতে পারবো না, but there are some limits where we can do some analytic calculation. আমি তাকে বলছি I can think of different regime when k is much greater than kg. What does that mean? That means the length scale is much smaller than the Jeans wavelength scale. Am I right? So there is a Jeans wavelength of the problem, and I am talking about length scale that are much smaller than the Jeans length scale. সেটা একটা regime. উল্টো regime টা হচ্ছে when k is much less than kj. That means we are considering of length scales that are much larger than the Jeans wavelength scale of that problem. So এই কিছু regime you can try to find some closed form analytic solution. So what we are going to now is we are going to take a simple limit when k is much less than kj. তাহলে সেটা যদি হয় তাহলে আমার ইকুয়েশনটা চেহারা ডেল্টা k ডাবল ডট minus 2a dot over a delta k dot plus cs square by a square minus kj square delta k equal to 0, approximately equal to.
My research area is in the interface of astrophysics and cosmology. To be more specific, actually I work on cosmology, which really tells us about the evolution of the universe, so how the universe started, what is the content of the universe, and what is the future of the universe. And I have been teaching cosmology course, for example, in both undergraduate and master's level for the last 5-6 years at Presidency Physics. But my particular research area actually looks into how supermassive black holes. So we know black holes come in two different mass ranges. The ones that are few times the mass of the sun are called stellar mass black holes. The ones that are 10 to the 6 to 10 to the 9 times the mass of the sun, they are called supermassive black holes. And in the paradigm of galaxy evolution, it is now known through several observations that at the center of every massive galaxy in the universe, these supermassive black holes exist. And also, there is another interesting aspect is that if we look at the total matter content of the universe, majority of the matter is in the form of dark matter. And what is meant by dark matter? It is matter that doesn't have electromagnetic interaction. So they only interact gravitationally and they can have weak interactions. But there is no electromagnetic interaction, in contrast to how we are made or how stars and galaxies are made, which are luminous matter and have electromagnetic interaction. So it turns out that the universe, now in the context of structure formation or galaxy formation, it is believed that in the universe there are these big clumps of dark matter which we call dark matter halos, and then inside these halos galaxies form, that means luminous matters form or stars form, and you make galaxies. So we have dark matter halo, within the center of it we have galaxies, and now at the center of every galaxy in the universe there is believed to be supermassive black hole. So my research essentially connects simulation aspects. So I run cosmological I work with cosmological simulations, I develop semi-analytic models, and then I compare with observations to try to set a connection between how dark matter, luminous matter and supermassive black holes evolve throughout the history of the universe. So that's essentially my research area. So I have been told to speak a bit about my achievements. Now before I get into that, I would just like to state a quotation from the famous Albert Einstein. So this was years back when I was a PhD student. I was reading the biography of Einstein and his thoughts and philosophies, and this fantastic quote that Einstein writes on education really touched my heart. So what it says is, the education of the individual, in addition to promoting his own innate abilities, would attempt to develop in him a sense of responsibility for his fellow men in place of the glorification of power and success in our present society. So it turns out that that was the quote I put in my thesis. So this is in the preface, I use this quotation of Professor Albert Einstein, and it's true that I kind of, in a way, very strongly feel that that should be the real goal of education. Of course, life is real or ideal goal of education. So of course life is not ideal, and it's a pity, it's very sad that we really cannot impose or make our goals of education in the lines in which Albert Einstein made this quote, but we still give it a shot. So I'm not sure what I should talk about my achievements, but I must say that some of the things that I have really enjoyed doing is writing my research papers. So far I have 15 published papers in refereed journal, in Astrophysical Journal, monthly notices of the Astronomical Society, MNRAS, Royal Astronomical Society, and PASP. These are the 3 journals where I have published so far. And I would say that I feel that the biggest achievement from my point of view is when I went to grad school, and then through my postdoc years, and then later when I am a faculty member in this department, I feel that the best achievements for me was when I met several brilliant individuals that include my mentors, my colleagues, and now my students, and what I learned from them, all in terms of life, how I should think about science, how should I think about a career, how should I mentor students, how should I see myself, my own perspective of what my role should be in society, in life, actually came only when I interacted. I wouldn't say it came only when I interacted with these brilliant people. It came through a lot of learning processes. But these brilliant individuals whom I met, and I'm so lucky that I met them and I'm meeting them every day in class, actually makes me feel that I have achieved a lot. So if I have to talk in terms of prizes and all that stuff, they are all in my CV. But yeah, I was awarded some prizes because of good results in my school and college level exams. But as I said, that quoting again Professor Einstein, I must say that achievements for me are definitely what I learned throughout my years of growing, throughout my years when I stayed in a foreign land and interacted with different culture, and of course throughout the days when I have been a faculty member, developing this department. So that's achievements for me, but I would rather feel very proud to speak about the achievements of my students whom I mentored. So it's a very, very proud privilege for me to tell that several of my bachelor's and master's students, just not mine, but many of the bachelor's and master's students in this department, right after we changed our curriculum, we made a transition of our curriculum, several of them led fantastic research papers in leading journals of the world. Some of my students published and actually wrote first author papers in the Astrophysical Journal or the monthly notices of the Royal Astronomical Society, two of the top journals in our discipline. And in total, if I combine the contributions of all the BSc and MSc students who worked with me and my colleagues in the last 4 years, since 2015, we have close to 30 publications from our students. These are journal publications, and on top of that there are many conference proceedings. And I would just like to mention two of the fantastic top-notch international prizes that 3 of my students got. So 2 of my students were awarded the Distinguished Student Award from the American Physical Society, and both of them are now PhD students at, one of them is a PhD student at University of Maryland now, just graduated last year, and another is a student at Yale University. So they were awarded the APS Distinguished Student Award, and with that award they went and presented their research work in the 2018 APS March and April meetings respectively. So that's a very, very proud privilege and proud achievement I consider for me. And these are actually the top most achievements, the international achievements my students have achieved in all frames, in national level, in state level, competitions and everything. I'm not going into that. And the other one, the recent one, this was MSc first year student, his name is Suchetana Chatterjee, and he was awarded, this is the first time someone got this award from Presidency Physics. It's from the Indo-US Science and Technology Forum. It's called the Suchetana National Scholarship. So he was given this award, and this summer right now he has been working with Professor Raja Gohakurta at UC Santa Cruz for his internship. And as I said, that through these I feel that I have accomplished a lot. The other aspect of accomplishment I would like to talk about is the number of courses I have taken and the curriculum design that I was part of. So far I have taught about 15 courses, and I really don't like to keep teaching the same courses again and again. So maybe a couple of times, 3-4 times, and then I'd like to teach a new course because that gives me ample opportunity to learn. And so teaching these classes, interacting with students, learning from my peers, my mentors and my students and colleagues, and seeing my students achieve so much is what I consider my greatest achievement.